Hey everyone, let's begin. This will be an overview of dynamics. If you're in an engineering school, you're probably taking engineering mechanics, which is broken down into two courses over 2 semesters. The first course will be known as statics, and then the second course is dynamics. So what we'll cover today is an introduction to dynamics. All right, so we start off with classical dynamics, and then we have particles. Particles are used in modeling approximations. So we refer to them or see them as volumeless masses or mass points. Um, a rigid body is another modeling approximation. So this represents a body that just never deforms. Okay, that takes us to kinematics. When we get to kinematics, this is going to be for us the study of motion. Kinematics is the study of the causes of motion, unbalanced forces on some object. Absolute and relative motion refer to the frame of reference used to study motion and whether it's fixed, right, meaning absolute, or moving, which is relative. Um, Kinetic analytical methods are based on Newton and Euler's laws that you've heard of, Euler's laws of motion, and they're called force, mass, acceleration, work energy, and impulse momentum methods. So let's dive into a quick review of vector derivative calculus. Vectors and vector math for us will be prerequisites to understanding this course in dynamics. So vectors can be written as functions of scalars. All right, so we'll say A of u, and then if u changes, let's state that if u changes by delta u, then we'll say A changes, right? And if that's the case, we have A of u plus delta u minus A of u. All right, so then if we take the derivative of A, and I'll write WRT for with respect to, WRT is with respect to u, then here's what we'll do. If you recall, let's see, let's take the limit as delta u approaches 0, the limit of A of u plus delta u minus A of u all over delta u. Okay, so then the magnitude of the derivative, and the derivative of the magnitude, right? These two terms, magnitude of the derivative and derivative of the negative of the magnitude, sorry, these are not the same quantity, right? This might be confusing if it's not mentioned explicitly. So I'll show it here. Right? These are not the same quantity. All right, now we're taking a look at position. Position is the location of a particle at an instant in time. Right? The location of a particle at an instant in time, but we have to say that it's relative to an origin. Relative to an origin. So it's given by a position vector. We'll say R of t. A difference between the locations at 2 times. So let's say a difference between the locations at 2 times, R of t and R of t plus delta t. this will be for us displacement vector. Displacement vector delta r. So delta r is r of t plus delta t minus r of t. All right, so the path coordinate for us here is the distance down the path. Distance down the path that the particle had traveled by time t. So distance down the path that the particle had traveled by time t. All right. So again, delta s equals s of t plus delta t minus s of t. Note that the path coordinate is a scalar, not a vector. So the path coordinate is a scalar, not a vector. All right, and now we can say that the path coordinate is not necessarily the same. So I'll write that out. The path coordinate, so not necessarily the same as the distance the particle has moved. So it's not the same as the distance that the particle has moved. All right, so what does that mean? Let's show an example. So if a particle moves forward, what do we want to say? Let's just say 5 units, right? It moves forward 5 units and then it stops and maybe it just goes backwards, right? Then it goes back 5 units. And this is all in time t. All in time t. All right, we'll say that the path coordinate is 0. While we'll also say that the distance for us is 10. Taking a look at velocity and speed. Velocity is the vector indicating the change in position with respect to time. So velocity is the vector indicating the change in position with respect to time. So we'll have v of t is equal to the limit of delta r over delta t as delta t approaches 0. So velocity is also noted as such, where the dot above the position vector indicates differentiation with respect to time. So the dot above the position vector for us indicates differentiation with respect to time. The velocity vector is tangential. The velocity vector is tangential to the path at all points and times. All right, the magnitude of the velocity is called the speed. So it's defined as the derivative of the position with respect to time. It's defined as the derivative of the position with respect to time. Both velocity and speed have these dimensions. So careful accounting is really recommended to prevent confusion between them. All right, looking at acceleration. Acceleration is the change in the velocity. Change in the velocity, not the speed. And it's the change in velocity with time. And it's sometimes for us we can call it the change of the rate of change, the change of the rate of change. So mathematically looking at it, a of t is equal to the limit as delta t approaches 0 of delta v over delta t. All right, and then we'll have v of t with the dot, and then we'll have r of t with two dots. So the two dots, or I should say the double dot, signifies the second derivative with respect to time. Second derivative with respect to time. All right. So the dimensions, Lt squared. So units can be things such as meters per second squared, or maybe feet per second squared. All right. And then a of t does not have to be tangent to the path in the way that v of t does. So I'll write that out because it's important. A of t does not have to be tangent. Doesn't have to be tangent to the path in the way v of t does. So let's talk about Newtonian and newer mechanics. So we have Newtonian, or sometimes it's known as classical mechanics. Those are developed and published by Sir Isaac Newton in the late 1600s. So they contain some unlikely postulates, actually, such as universally fixed inertial frame of reference and time as an absolute throughout the universe. So then there is what we call relativistic mechanics. Relativistic mechanics. It's a later development that removes those unlikely postulates. We have quantum mechanics, and quantum mechanics predicts the probability of events occurring and defines time as composed of quanta, or as discrete steps. So briefly looking at Newton's three laws. One, if a particle is at rest or moving with constant velocity, it will continue to do so unless acted on by an unbalanced force. Two is a particle acted on by an unbalanced force will accelerate in the direction of the sum of the forces. The magnitude of the acceleration is proportional to the magnitude of the force. The magnitude of the acceleration is also inversely proportional to the mass of the particle. And then there's the third. Forces of interaction between interacting particles will be equal in magnitude and opposite in direction. Right? We've heard for every action there's an equal and opposite reaction. Inertial frames of reference. So to measure acceleration, a frame of reference is needed. So we need a frame of reference. The frame of reference must be inertial. That is, it must be a rigid coordinate system that allows the use of Newton's three laws with acceptable accuracy. So again, it must be a rigid coordinate system that allows the use of Newton's three laws with acceptable accuracy. So what is acceptable will depend on the context of the application. So our example is on Earth, a frame attached to the planet. A frame attached to the planet is usually acceptable. It's usually acceptable. But in outer space, it will not be. In outer space, it will not be. Dimensions and units. A dimension is a quality that we say it can be measured. We look at length, time, mass, force. These are all examples of some dimensions. Dimensions are measured with standardized values called units. All right. Um, we can have meters, seconds, kilograms, pounds. They all correspond to the dimensions that I just wrote above. Two common systems are the US customary system and the SI system. So we say USCS or SI, or we may say metric system. The base units for the US customary system, for us, the base units are the foot, right? That's length, pound, force, and second, time. So pound is sometimes a unit of mass. When this happens, you must be certain to keep them straight. This is usually done by calling one the pound mass and the other the pound force, right? LBM and LBF. So the base units of SI system are the meter, right? The meter, kilogram, and the second as well. So we keep the units on all quantities clear in our calculations to avoid any errors. All right, mass, force, and weight. So force is related to mass by Newton's second law. His second law. So the second law is F equals ma. If a base unit in a system of measurement is force, then the mass must be derived from it. If a base unit is mass, force must be derived from it. So in the USCS, the unit of mass is the slug. So it's exactly 1 pound. Oops, that's 1 pound times second squared per feet. So this makes this system a gravitational system. In the SI system, the unit of force is the Newton. The Newton. So this is exactly 1 kilogram times meters per second squared. So this makes this system an absolute system. An absolute system. Weight. Weight is the force. Weight is the force, not the mass. The force that acceleration of gravity develops. And on Earth, gravity is about 9.81 meters per second squared, or we'll use 32.2 sometimes feet per second squared. Universal gravitation. So Sir Isaac Newton also developed the law of universal gravitation. This equation determines the force of attraction between any two particles a certain distance apart. So we have F equals G times m sub a m sub b over r squared. So again, it determines the force of attraction between any two particles a certain distance apart. Um, that g is the universal gravitational constant. It's not Earth gravity g, right? It's not Earth gravity g. It's 6.67 times 10 to the negative 11 cubic meters per kilograms times seconds squared. Here we have an example of gravitation. Our example says a 70 kilogram man is 6,378 kilometers above the surface of the Earth. What gravitational force does he exert on the planet? Well, first we know that the Earth has a mass of 5.9742 times 10 to the 24 kilograms. All right, so we simplify the law of gravitation. So we'll have F equals G m sub E over R squared. All right, then substituting values, we get F equals 6.67 times 10 to the negative 11. In the numerator, we have 70, 5.97 times 10 to the 24. And in the denominator, we have 6378 times 10 to the third squared. And in solving this, crunching those numbers, we get 686 newtons.